Let's start today's session. So what I plan for today is first we explore the few entries in the system folders. So let me first guide you the locations. Okay, so go to any of our tutorial. Let's say go to the cavity tutorial, square cavity. Okay, let's say 50 by 50. I'm picking. You pick up any folder. What we're going to do today is try to explore all the entries that is available in this 3 file, and along with that, when we move towards FV scheme, we try to explore the numerical schemes available in the OpenFOAM with the different options available, selection criteria and all these things. Along with that, when we go towards the FV solution file, we try to look at the different linear solver available in the OpenFOAM. So that is the idea. Let's first look at the control dict file. So let's open that file. Okay, so if you look at, there is a standard entries. Okay, but what different options available here? Okay, so right now we don't know. If we want to explore at each and every location what different options we have, then it is very easy. You just misspell this. So I'm typing few more word here. Let's say start time test. Okay, and let's save it. And when we try to run this particular case, so for that, let's first go to the directory, create the environment. Okay, let's check. Yeah, first we have to type a block mesh. Okay, so look, when we are typing even block mesh at that time also, it suggesting this entry is wrong. Okay, so what is the entry we have? It is start time, first time and latest time. So that many option is available at this location. So I constructed a one master file for that, and I will going to share with you. So it possesses so many entries that is available in the control dict file. So again, let's say we want to explore what different entry available at a stop criteria. Okay, so here again type, then check. Okay, so it giving you the idea at the stop level we have end time, next write, no right now and right now. That many options is available. Okay, so normally for a standard entries, OpenFOAM normally guide us what different option is available. So if you don't aware about the multiple options available at particular entries, no worry, you just misspell it. Okay, and the available options is listed in the terminal. Okay, so if you misspell it, it say okay, there is a fatal error. Okay, so don't worry about this type of output. So many time if you misspell it or there is a typo error, then definitely you're going to get this type of the error. Okay, but it is no worry about that part, and it sometime you will come to know what is wrong, and sometime even you don't know as well. So if you don't know, then it is very difficult to remove that type of error. We discuss later on all that aspect, but right now if you misspell it anywhere, okay, you will get a multiple entries. So if you want to check all the entries available in control dict file, so here is some master control dict file I created. Okay, so just give you the idea what different entries is available. Application is the name of the application that we're going to run, okay, the simulation, but it is not mandatory you give the same application. But if you are running, if you planning to run with the standard available script, then at that point of time this name is very important. Okay, now another entry we required the start time. So for the start time, OpenFOAM has a 3 options. Okay, one option is the start time, okay, itself. Okay, and you give the start time value equal to here. So let's say you want to start from 50 iteration, then give a start time and start time equal to 50. You want to start from the 0, then start time equal to 0. Let's say in your folder you have a multiple backups. Let's say you're running your case and maybe power failure, or you didn't give the enough number of the iteration, it stop, and you want to restart the run from the same location, that means from the last backup file, then start from you gave the latest time. Okay, so like that way you can change this entry and you able to start the simulation wherever you required. Okay, and this first time entry is related to earliest time step from the set of time directories. Okay, so whatever the earliest time step, if in your directories you don't have a 0 but you have 1 2 3 and 100, so it will going to start from earliest. Okay, so like that way you can manage the starting option in the OpenFOAM. Okay, then start time is you explicitly specify. Okay, then we have another important aspect where to stop. Okay, so end time. Okay, so end time, so you give the end time where you want to stop, or you have another option. Let's say simulation is running on, you think that right now I want to stop it, then use right now option and it will take a last iteration backup and stop immediately. Okay, or you can type as next write. That means when you say every 50 iteration you are writing the data, so before it reach the next 50 iteration, it write it and stop at that location. Okay, and no write now. Okay, so writing is off but it will stop immediately. Okay, so if you want write and now, that means you going to create a backup file at that particular iteration and then stop. If you don't require the backup file, then no write and stop now, and next write, that means when the next writing interval come, it will write and stop. Okay, then we require the delta t. Okay, it is a steady state simulation, so delta t value is immaterial. Then writing control, this is very important aspect. Okay, how we can write our simulation data. Okay, for that different options is available. Writing options. Okay, for that we have a writing control. For that we have a time steps. So normally we go with the time step. Writing data every write interval of the time step. So whatever the interval we give, at that every 50, if we gave here every 50, it will write at every 50 time step. Okay, so like that way it going to work. Then runtime, so write data every write interval about the runtime. Okay, so you say 0.01 is the write interval and specify runtime, so every after 0.01 second it going to write the data. Okay, so like that way you have a multiple options available. Then adjustable runtime, so when you are working with, let's say, pimple type of the algorithm, at that time based on the current number setting, you have a leverage to manipulate the or give a flexibility to the delta t. You can run two ways: either you fix the delta t and allow the current number to be computed, and other way is you fix the current number and allow the simulation to change the delta t. So if you say that my current number not going to go below more than 1, then delta t automatically adjusted so that current number during entire simulation never go beyond 1. Okay, so like that way if you are working with this, at that time we require the adjustable runtime as a writing control, and immediately whatever you write here at every, let's say, 0.01 second, it going to write the data. Then another is the CPU time, write data every interval with respect to CPU time. Okay, wall clock time. So but we normally don't prefer these two options. So if you are working with simple type of the or steady state simulation, then time step and writing interval. Okay, as well as piezo, then you can type runtime and writing interval, or time step and writing interval, no worry. Okay, or if you are working with adjustable runtime, then adjustable runtime and the writing interval. Okay, so that is few entry we have to take into account while we are working with the OpenFOAM. Then purge write. Okay, so purge write is allow you to store a data. It give you the backup. What backup? You can say that say after every 50 iteration we want to create a new backup. Okay, but if you are not interested to entire simulation backup, then you increase this purge write equal to, let's say, 10. Then in your directory, what is your directory? That means from where you are running this case. Right now it is in the grid 50/50 from where we are running. When the simulation start, if you keep purge write equal to 0 and it going to run up to 2000 iteration, then after every 50 interval you will see the backup file here. Okay, but you think that is too heavy for as far as storage is concerned, then you can say purge write equal to 10. So at a time you only have a 10 backup inside of this directory. What it mean? That mean that, let's say, purge write equal to 10. Okay, so what it going to do, after every 10 iteration it going to store the data 10, 20, 30, 40, 50, and let's say you kept purge rate equal to 5, then when it's try to store the data for 60 iteration, it will going to delete the data for 10th iteration, 70, then 20 iteration data gone. Okay, so like that way it only allow within that particular directory at a time 5 backup other than the 0 folder. Okay, then another aspect is the writing format. Okay, so ASCII it is readable and binary it is in the machine language. Okay, so if you are working with the turbulent flow type of the case, then it is better to go with a binary type of the thing. Okay, and why? Because it will take very less amount of hard disk memory. Okay, so depending on your requirement, and even it is faster as well. Okay, so normally IO is very time consuming, please understand that way. In any of the simulation, either you are developing your own code and simulating, or you are working with the, let's say this OpenFOAM. Okay, any place IO, that means input output. So wherever you required, only at that point of time you dump the data, that means you take a backup. Okay, let's say you are pretty sure your simulation not going to diverge and you only require the data after the steady state. Okay, and if you are working with a very large mesh size, I'm saying large mesh size, that means something like 2 to 3 million mesh, then it is not advisable to write a every 50 iteration. Okay, no, because to writing a data in the hard disk is the most time consuming aspect of the simulations. Okay, so avoid as much as you can, but right now we are doing all the testing, so no worry. But when you start your real simulation with the OpenFOAM, be careful with this IO. Another aspect is the precision. Okay, so 6 digit is normally sufficient precision. Okay, but if you think like you are working with a micro channel and your velocity or any of the, let's say, species concentration is very very low, at that point of time you have to may increase this precision. Okay, so you will reduce the round of error. Then write compress. Okay, so if no, then there is uncompressed data. If write compress equal to yes, then you get a zip file. Okay, for all your backup files. Okay, so like that way you can check, or sorry, in not check, but in like that way you can save the hard disk memory. Okay, then time format is normally the general format. Okay, so when it is general, that means the scientific way, the normal format of writing the time. Okay, then time precision is also be available. Then runtime modifiable true. It is very very important that we kept runtime modifiable true. Why? Because when the simulation is going on, and if you want to change parameter while simulation going on, like if you want to change the relaxation parameter delta t, let's say writing interval, okay, as well as the end time, okay, whatever you want to change, you can change while the simulation is going on. Okay, so that's why it is very good if you retain this as a true. Then when, as I told you, when you are working with the pimple type of the algorithm, you have flexibility to change the delta t, but fixing the current number. So at that point of time, this few more entries is available, like adjustable time step, we can say yes. If you say no, then it again try to fix this delta t whatever you specify here. Okay, if you say adjustable time step equal to yes, then it will calculate the time step depending on the current number whatever you specified. Okay, and maximum delta t is, this is the limit. Okay, so even though, let's say you say maximum current number is equal to 1, okay, and you set the maximum delta t value 0.001, okay, but for this current number maybe maximum delta t goes 0.01 as well. Okay, but you are fixing that maximum value of delta t from here. So either it reach the maximum limit or it reach the current number limit, it will fix this flexible delta t. Okay, and it is every iteration it will calculate the new delta t, and like that way your simulation going to be progress. So this is a good idea when you are working with a transient simulation with a let's say turbulent flow enable, or let's say FSI, or maybe let's say multi-phase flow, or all that regard. We don't know beforehand where the velocity is going very pretty high, and sometime let's say some places very narrow portion is available in your geometry, so immediately velocity shoot up and current number shoot up, and maybe simulation may diverge. So it is better to work with adjustable time step, but this adjustable time step option is only available with the pimple type of the algorithm, but you can immediately modify piezo algorithm with the adjustable time step enable. Okay, so there is a very quick way you can fix that also, but right now by default whatever available is with the pimple algorithm only. Okay, now along with this standard entries, okay, sometime we also require some dynamically linked libraries. Let's say you created your own new library for boundary conditions. Okay, let's say we require some oscillatory parabolic inflow boundary conditions, so that is not readily available. For that we have to code our own library, and that library we have to link dynamically. What is dynamically? While this code is running, at that time it will try to adapt dynamically whatever the variable and whatever the calculation we are going to put in that particular subroutine, it try to execute. Okay, so it is called dynamically linked type of the library. For that purpose you require this keyword libs and whatever the name of that library you want to plug in inside the OpenFOAM. So for that few more entries is required, like libs and that particular library name. Then now it is the functions. Okay, that is the standard way to look at the co-processing and take a multiple outputs. So in control dict we have a few more entries related to function you can keep, like inflow outflow calculations. Okay, this all entry we will explore when we look at the function object. Okay, but right now I want to give you the idea that all this function object and everything is going to be set at the control dict level. Let's say you want to create a probes, so that is also available here. Okay, so this all entry is available at this location. Okay, so many entries is available, so many options is available at a control dict level to manage our simulation, to control the simulation, to create a better output for post processing purpose. All these things is available at a control dict file level. Okay, so this few entries later on each one we going to explore. Okay, in the function object when we start discussing, at that time I give you the brief idea about all this function object. Okay, so right now please understand few entries allow us to control the control dict file. Okay, so that is what about this control dict file. And if you want to explore each and every options in detailed way, then I suggest try to read our user manual, and I will give you the page number. It is 113. Okay, so from 113 page you can see the time and data entry whatever is available in this entire control dict file. Okay, so I suggest please walk through it, it give you the better idea. Okay, so try to read it all these entries and it give you the idea what different entries is available at a control dict file level. Okay, so this is all about the control dict file. Okay, let's now explore few entries inside the FV scheme file. Okay, so let's open the FV scheme file. Okay, so this is our standard FV scheme file. Let's say we don't know what different entries available at a FV scheme file. Before we go towards this FV scheme file, different entries, let me brief you about this FV scheme particular file. Okay, so with the help of this FV scheme we able to set a numerical scheme for all the terms that is available in any of the equations, and that equation is coded in terms of certain algorithm inside the OpenFOAM. Let's say right now we are working with the fluid flow phenomena, so our equation is Navier-Stokes equation and continuity. So if you remember from your basic, so Navier-Stokes equation contain the temporal derivative, gradient term, divergence term, Laplacian terms. Okay, so all the terms we want, for all these terms we require certain class of the discretization scheme that we able to set with the help of this FV scheme particular directory. Okay, so if you see typical let's say typical entry inside of this particular FV scheme, then you can see that DDT scheme that is related to temporal derivatives, then gradient scheme, then divergence scheme that is related to the convective part, then Laplacian scheme, some interpolation scheme is required, then surface gradient scheme is required, this wall distance is required if we want to calculate certain turbulent quantities. Okay, at that time it is required. Okay, normally it not required. So this is few entries is available at a each at a FV scheme level. Okay, now let's explore what different options available at each of these entries. Okay, so I created one of the master file for that. Okay, so let's explore few of these entries that is available inside the FV scheme file. Okay, so let's start with this DDT scheme. Okay, so DDT scheme allow us to fix the temporal derivatives. Okay, so temporal derivative, you understand, del by del t of any of the quantities. Okay, so that scheme is available, and we have a certain options like Eulerian scheme. If you select here, okay, what it means is first order implicit scheme, then local time step first order implicit scheme, then Crank-Nicolson second order implicit, all are bounded schemes. Okay, then backward if you type, it is a unbounded second order implicit scheme, and steady state, that means no temporal derivative going to be calculated. But few control we have with the Crank-Nicolson scheme. If we set the psi equal to 1 corresponding to the pure Crank-Nicolson, okay, and if we say psi equal to 0, it's corresponding to pure Eulerian scheme. Okay, so if you type 0.5, it is it in between of the Eulerian and the Crank-Nicolson scheme. Okay, so based on your requirement, you can tune this DDT scheme. And normally what I observe, if you are working with, let's say, simple flow, that means let's say without any turbulent or any multi-phase flow or anything, then I suggest stick to the either Eulerian scheme or backward type of the scheme. But when you go towards turbulent type of calculation, then this Crank-Nicolson scheme give you that added advantage in terms of the selecting the delta t. Okay, so depending on your physics, you can choose this type of the scheme. Okay, now after that we have an entry about gradient scheme. But before we move towards gradient scheme, very important aspect required is the interpolations. Okay, so first we check that and then we come back to that part. So interpolation scheme normally allow us to interpolate the values from cell center to the phase center side. Okay, so for that we have a total 4 category available. One is the standard category, or with the help of that it is generalized scheme basically. Okay, so where we have a linear, it is nothing but the center difference second order scheme or center difference scheme. Okay, then cubic corrected and the midpoint. Okay, so this two is called the central difference type of the scheme available. Okay, then in the interpolation we require the upwinding type of the scheme, TVD type of the scheme, and NVD type of the scheme. But all these schemes normally people don't use for general interpolation purpose. Okay, but normally if you see in the OpenFOAM, people try to work with the linear is the best choice as far as this interpolation scheme is concerned. But they give you the certain flexibility. You can choose even upwinding scheme also, but it is not a realistic choice. Okay, so if you want to look at the default entry, then for generalized scheme it is a default linear. Okay, when you type just linear, it understand that it is center difference type of the interpolation is required. Again, this interpolation is from cell center to the phase center. Okay, so like that way we are creating the interpolation. If we are going towards, let's say, convective specified scheme, okay, so it is related to this upwinding type of the scheme. At that point of time we require the direction of convection. For that we require the flux, and normally we calculate the flux based on the phi. Okay, and based on the direction of the phi, it try to change the weightage from parent cell towards the neighboring cell. Okay, in the calculation of the interpolated value at the phase center from the cell center. Then we have a certain limited scheme is also available. Okay, so this limited linear scheme, okay, is allow us to limit the contribution. Okay, so it is best choice is something like phi equal to 0 to phi equal to 1, and normally recommended is phi equal to 1. Okay, it is a generalized recommendation to work with the limited linear type of the scheme. Okay, then we have a limited Van Leer scheme, where this scheme normally people use for a scalar type of the interpolations. Okay, and here you have a chance to specify the upper and lower both the limit. Okay, so here you can specify upper and lower limit. In between they try to bound the particular scheme. Okay, and if you this is a its sub classification of this scheme is limit between 0 to 1 only. Okay, so it is by default Van Leer 0 to 1 scheme. Okay, if you are stick to the only vector quantities, then there is a special class of scheme is available, limited linear version V. Okay, V represent that it is only applicable to the vector quantities. How it going to work? If you not specify vector V, then each component of your vector it try to limit, okay, or it try to based on this phi. Okay, that means flux we calculate for based on each direction. Okay, and then from that we try to create the limiter. But if you want that for each component, we don't require the separate limiter, but we want the uniform limiter for all the component, then we go with the limited linear V. Okay, and when we say limited linear V, the OpenFOAM understand they only have to calculate one time limiter or one time its contribution, and based on that it try to apply to all three component of velocity if we are talking about the velocity. So that is special version of the scheme is available as far as the interpolation is concerned, but normally these all the schemes people not going to use for normal interpolation purpose. So in the interpolation scheme, if we want to look at the simplified version of the scheme, it is the best scheme I can say. Okay, default is linear straight away. Normally we going to work with this default linear type of the scheme as far as the interpolation is concerned. Along with this we have a surface gradient normal. Okay, so normally we require the surface, we have to calculate the gradient at a face center, and then we have to take a normal component of that particular gradient. So it's called the surface gradient normal scheme. Okay, so sun grade scheme, and for sun grade scheme when we are taking the normal component of that gradient, we have to take into account the skewness of the element and all these things, and at that point of time we have certain options is available, like if we use uncorrected, what it means, it is not going to take into account the non-orthogonal correction. Okay, and corrected, that means it's going to take into account the explicit correction, and limited, that means how much percentage of correction you want to take into account. If you say limited 0 correspond to uncorrected, limited 1 correspond to explicitly corrected 1, and if you want to blend in between, then you choose the correction factor. So best choice is corrected. Okay, so if our element is highly skewed element, or we don't know either at any location it's going to be skewed or not, so better always try to work with the default corrected. Okay, then we never going to come across the problem about the non-orthogonal correction part. So it is the best choice is the corrected one. Okay, then along with this we also have to specify certain gradient scheme. Okay, like if we want to calculate let's say pressure gradient term in the Navier-Stokes equation, for that purpose we required certain gradient schemes. Okay, so as far as the gradient scheme is concerned, we have a certain options available, like Gaussian scheme available, least square, fourth, cell limited and face limited. So that many options is available, but normally we try to stick to the Gaussian and its interpolation scheme. Okay, so Gaussian second order, it is second order, and Gaussian integral is the way to go. So gradient scheme, so if we want to specify gradient for pressure, we say Gaussian linear. This interpolation come from where? This interpolation entry is coming from this. Okay, so you can select this interpolation from here. Okay, this is the default interpolation scheme, so you can apply that scheme wherever there is a interpolation options we required. So Gaussian, and Gaussian is the keyword required. Okay, so Gaussian and the interpolations. So here interpolation scheme you can choose from the whatever I showed you. Okay, so that is how you can see. If you don't want to work with the Gaussian type of the scheme, then let's say cell limited, then gradient of u cell limited, then Gaussian scheme and linear. Okay, so like that way you can select the different class of the gradient scheme that is available with the inside the OpenFOAM. We also required certain other class of the scheme that is called the Laplacian scheme. So this is, let's say, our term in Navier-Stokes equation. So when we write in the our code, we say Laplacian nu into u. Okay, we assume that here kinetic viscosity is constant, so we take it out, so we have a Laplacian operator into u. So for this, let's say we want to select the scheme. So what different options available? We have a corrected, same interpolation schemes. Okay, so for the Laplacian, what we only have a choice is the Gaussian scheme. We don't have any other options, and this is the syntax for this. Okay, for any of this term we require this syntax. That means Gaussian is the choice, then Gaussian and interpolation. This interpolation scheme is required to interpolate the kinematic or this diffusion constant. Okay, so normally diffusion constant calculation, let's say here it is a constant, so no worry, but it is, let's say, depend on depend on temperature or something. At that time we require the rigorous interpolation. So Gaussian interpolations, this interpolation is for diffusion constant, and sun gradient is for gradient of, let's say in this case is u, grade u. So for that you can select the interpolation scheme from the interpolation part and the sun gradient scheme from the sun surface gradient part, and you can create the entire scheme. So if you look at here, those for Laplacian, Gaussian, linear. So linear is the interpolation and sun gradient is the corrected. Okay, so in the one of our cavity case, we look at it is orthogonal, correct, it is not a corrected. Then we, even though we refine the non-orthogonal iteration correction in the simple algorithm or piezo, we unable to convert the skew cavity because it is not a corrected one. Okay, so that is the best choice, linear and the corrected. Linear is the interpolation, please understand this is the proper syntax. Okay, it is two part. Interpolation scheme, it is for the diffusion part, any of the diffusion coefficient, and sun gradient is for the gradient component or the gradient of that particular quantity. Okay, so like that way you can select, and for this Laplacian of nu into u we have a Gaussian, linear and corrected. Okay, so that is the choice we have. So if you misspell it, okay, you get a certain class of options available in this particular thing. Okay, then after this Laplacian scheme, very important scheme for numerical calculation in fluid flow is the divergence scheme, or the scheme related to convective parts. So let's say what entry we have is the divergence scheme, and let's say for Navier-Stokes equation this is its term. Okay, out of this, in the algorithm or in the code, we are going to write divergence of phi into u, and phi we consider as a rho u. Okay, rho u is the flux, okay, and u is our vector. Okay, so divergence of phi u, and now we want to select the particular scheme for that. So keyword is Gaussian only that choice is available we have. Okay, and along with that we have to select the interpolation scheme. So again, this interpolation scheme, you can select the interpolation scheme from all the entries available at interpolation scheme level. Okay, so now we are going towards the convective type of the scheme. So you can select either generalized schemes or convective dominated or convective limited type of the scheme. Either any of this scheme you can able to choose for this thing. Normal choice is linear scheme, then it is if you behavior wise if you see, then it is second order and unbounded scheme. Skew linear, second order, more unbounded, skewness correction is applicable. Okay, cubic corrected, fourth order type of the scheme but unbounded. Upwinding, first order bounded scheme. Linear upwinding, first order and the second order in between, and bounded scheme. Quick is again first to second order. It is depend on the why it says first to second order, because it's depend on your discrete grid size. Okay, as if you are working in uniform mesh, then it behave like a second order. If you are going towards non-uniform mesh and an unstructured mesh, is go from second to the first order, and it is all bounded scheme. TVD scheme, then SFCD scheme, second order bounded, then NVD schemes is also bounded schemes. Okay, so this bounded scheme normally give you the much stabilization. Okay, but the linear scheme is highly unstable scheme. Okay, so but normally how it goes is something like this way. If you are working with the turbulent type of the flow, then I suggest go with the linear scheme. And when you go towards the linear scheme, make sure your mesh size is supposed to be very, very fine. Okay, and if then also you're not able to stabilize the flow, then this is the how one has to proceed. First they going to work with the very highly diffusive scheme, that is upwinding scheme. Then from upwinding go towards the linear upwinding scheme, and then from linear go towards the linear scheme. Okay, so that is the, I say, best way to look at the convergence. So sometime it is not very quick that immediately you get the convergence for, let's say, very highly turbulent flow with the mesh sizes of very high number of elements, and near wall boundary treatment is also very fine. That means we are giving very fine mesh near the wall at that point of time. It is very difficult to get a convergence with the linear scheme. Okay, so then you have to start with the upwinding, then go to a linear upwinding or quick scheme, and then move towards the linear scheme. Okay, so this is about the divergence schemes that is available. Okay, so the last part is in this sometime we require the few more entries like flux required. Okay, so this flux required subdirectory allow us to specify for what particular variable we have to store the flux. Okay, so for that purpose, if we are working with the predictor corrector algorithm, so always we require the flux for pressure. Okay, most of the time. Okay, so flux required like piezo type of the algorithm, it's always required this flux calculation. So at that point of time this entry is always be there. Otherwise if you forget to keep this entry, no problem, OpenFOAM immediately give you the idea, it give you the fatal error saying okay, flux required but it is not specified in the FV scheme file. Okay, so that immediately you can specify this. So this is the few entry you can see inside the this FV scheme file. Sometime if we let's say you are working with something like solid movement type of the algorithm, at that time you require the scheme for second order time derivative. Okay, so for what I mean to say is, right now if you see we have a first order time derivative, same way we have a second order time derivative, but for that only one scheme available is the Eulerian scheme. Okay, so for second order if you want to specify, then it is d2 dt2 scheme. Okay, so I just type it down here so you remember. If for second order if you want to go, then it is very simple way, you can type d2 dt2 scheme and then entry is the Eulerian scheme. Okay, so that is how one can set the scheme. So all the schemes whatever required you have to set in the FV scheme file. Okay, now let's move towards algorithm aspect of this OpenFOAM. Okay, so that all the entry related to the linear algebraic calculation or number crunching calculation is goes towards the FV solutions. Okay, so in FV solution we have a certain entries like solver is the first entry, then we have a relaxation, then we have piezo pimple algorithm based key entry is also available. Okay, so few entries is required at this FV solution. First entry always solvers. Under the solver we have a sub entry like solver for PU and all this thing. Along with that we require entry for relaxation factors, piezo and pimple algorithm or simple algorithm. Okay, so first let's look at the solver entries. So as far as the solver is concerned, we have certain choice available. So based on the conjugate gradient type of the linear solver, we have a two option. One is the preconditional conjugate gradient PCG for symmetric matrix, and preconditioned by conjugate gradient then P by CG for asymmetric matrix. Okay, so either PCG or P by CG. So for pressure always goes PCG, for velocity always goes P by CG, because when we discretize the pressure equation is always behave as a symmetric matrix, but here it is behave as asymmetric matrix. Okay, then we have a smooth solvers available like Gauss-Seidel and all this type of solver. Then we have a generalized geometric algebraic multigrid type of the solver options is also available, GMG. Okay, and diagonal solver for explicit scheme writing the diagonal. So normal choice is something like this way. For pressure, normally we go with the PCG or GMG, okay, and for velocity we go with the BiCG, okay. As compared to the smooth solver, BiCG give you the very fast convergence, okay. So stick to the BiCG as compared to this. So if you look at the entry in, let's say, P solver, okay, solver for P, we have to define the solver is PCG, then precondition, because it is preconditioner conjugate gradient, so preconditioner available choice is DIC, okay. So DIC is diagonal incomplete symmetric preconditioner, okay. So that is choice is available, and along with that we require certain few more entries. So one is the tolerance, another is the relative tolerance, okay. So if you see entire calculation, we have a chance to stop the simulation by three ways, okay. One is this residual fall below this solver tolerance, okay. If the residual is fall below this solver tolerance, then the linear solver stop, or maybe the ratio of current initial residuals fall below the solver relative tolerance. What it mean? The ratio of current to the initial residuals, okay. So whatever the current residuals we have, we can scale down that residual with the initial residuals, and if that ratio is fall down below the 0.01, then we can stop the simulations, okay. So or we can specify the max iter. So normally by default value of the max iter is 1000, okay. If you don't specify, then by default value is 1000, and if you don't specify min iter, then its value is 0, okay. So minimum iteration is 0, but that means when the solution is almost converged, at that time it is not necessary that linear solver take more than some number of iteration. But if you want to think that no, minimum that many iterations supposed to take, then you can fix this entry also, but it is an optional entry, but this entry is mandatory, okay. So relative tolerance is little bit relaxed condition as compared to the residuals actual check, okay. So normally what people do is something like this way. If you are working piezo or pimple type of algorithm, and if you have a n character equal to more than 1 and 2, okay, so for first few character they go with the this setting where they try to check even for relative tolerance, and for final correction, like here I gave, relative tolerance goes to 0, okay. So that means it explicitly going to check that absolute tolerance or the residuals fall, when the residuals fall below this solver tolerance, at that point of time it will try to stop, okay. So in all this case we require the preconditioner. So for preconditioner, normally this many options is available, okay. Now let's look at another solver is GMG, okay. So geometric algebraic multigrid solver. If for pressure, it is very fast solver, okay. So normally I prefer to go with the GMG as compared to PCG for pressure, okay. So GMG is pretty fast, and for that also few entries available, okay. Tolerance, relative tolerance, then smoother, okay. Sometime we have to give the smoothing for GMG, okay. So at that time smoother is required. Pre mesh coarsening step and the post processing step we require, okay. So for that few entries, and merging level, so by default it is, or always keep as a 1, but if you think it's you want much speeder, and for regular mesh like Cartesian type of mesh, you can go with a higher level of merging as well. So GMG normally how it goes, it first take the your provided or whatever the mesh you created, it try to take that mesh, okay, and it try to do the coarsening, and number of cell in a coarsening level, this is you can restrict that it is 100. That means this particular GMG not go below the 100 number of the cell. That means let's say you have a 10,000 cell, but if you restrict it to the 1000, that means your coarser mesh not go below the 1000 element, okay. So like that way you can specify. So GMG how it going to work, it try to coarsen the your mesh at a matrix level, okay. You need not to do anything while they construct the matrix. At that point of time it try to coarsen the mesh at the matrix level, and first it try to take a create a result on a coarser mesh, then they map the mesh on the finer level, and finally it give you the result on the finest mesh. Okay, but it is entirely going inside the particular this algorithm, so it is completely redundant. So whoever developing this class of the solver, they have to understand all this detail behind this, how the GMG work and all this thing. If you ask me, I never work in that area. Okay, so I may not able to defend your critical questions about this GMG solver. Okay, who exactly work on the GMG, they only able to specify or clear certain class of the questions. Okay, but few things is mandatory, is something like tolerance level, okay, as well as this smoother, and then sweep, and this merging level. Okay, for smoothing you have a certain options available. For here Gauss idle, as compared to that DIC and DAC Gauss idles, this options is available. Okay, so along with that we have a selection for solver for all the variables, like u, if you are working with the, let's say, turbulent flow, then omega k equations. Okay, so you can specify multiple ways the solver setting. It's not necessary you can, for each variable you can specify, you can go like this pipeline type of way at a time. If you are sure that for all this variable you want to give a same setting, then at a time you can specify. Okay, and then later on, let's say for particular thing, if you want to change the setting, then you can change the setting as well. Okay, so here I gave you entire different entries. Okay, how you can set different things. Okay, so then along with that, few more entries required is algorithm specific. Okay, so let's first see the simple algorithm. So for simple algorithm, you have a non-orthogonal correction. So this correction value, how much is sufficient? There is no answer for that. Okay, because it depend on the mesh. So how it normally work, you try to start with something like 2 or 3 value, till it not going to converge, then increase the values. Okay, and people go up to 20 correction as well. Okay, so no worry about that part. So it don't think that it is too heavy. No, people go up to 20 correction as well. Okay, so that is what I say. Then sometime we require this reference cell for pressure, and reference at that particular reference cell we require the pressure value. Okay, so if you're not specifying explicitly at any of the boundary the pressure, then this condition supposed to be unable. Okay, consistence equal to yes, that means simple C algorithm going to be work. If not, if you don't specify this, then by default simple algorithm going to work. Then we require the certain residual control, okay, for each of the variable. Then we require the relaxation factor for field and for equations separately. Okay, so that is how you can specify the certain relaxation parameters. Okay, then let's look at few entry for piezo algorithm. For piezo we require n correctors and on non-orthogonal corrections as well, and this entry. Okay, so that it's very simple setting, but please understand, for piezo we don't have a choice of relaxation factor. Okay, so if you gave any relaxation, it immaterial for piezo algorithm. Okay, then if you bundle piezo and simple, that means in the piezo you add the functionality of relaxation as well as you can correct the outer corrector, then it come as a pimple algorithm. So in pimple you have a n corrector, non-orthogonal corrector, over that you have a outer corrector. Okay, along with that you have p cell entry and sometime momentum predictor. Yes, okay, so you can activate the momentum predictor. So normally how it goes for compressible flow, it you have a leverage to calculate the momentum predictor by this switch. Okay, you don't want, then say no. And when you specify the pimple, at that time you have a chance to also work with the under relaxation factor. So that's why with the pimple you also specify this relaxation parameter, and it will go very nicely with the pimple. So this is few entries available at a FV solution level. Okay, so what we cover in the very quick way is few entries in the control dict file that will allow us to control the entire simulation. Then FV scheme, what different type of the numerical schemes options is available. If you want to check, then you can go towards the FV scheme file, and different linear solvers as well as the algorithm based solver available, and its entry is available in the FV solution file. Okay, so all this master file I'm going to share with you, so you also have the same entries with you. Let's say you want to explore a few more things about this FV scheme. Okay, then I suggest please try to look at the user manual, and there is a numerical scheme, one very detailed discussion they gave. Okay, but if you are interested about all the discretization, exact equation and everything, okay, then we have to dig in a couple of publish paper, as well as whoever the founder and co-founder of this particular entire OpenFOAM, they publish their own thesis. Okay, so I have a couple of theses, so I will upload, and if I'm not able to upload, I give you the link from where you are able to download that particular thesis. Okay, and in that particular thesis they explain in the very detailed way all different class of the schemes and all these things. Okay, so I will try to provide you the material, and you read it if you are interested in going in much detail about how the linear scheme is coded inside the OpenFOAM and all that aspect. Okay, so that aspect you can see from that different thesis and different PDFs. Okay, if you want to look at the solution algorithm entries, that is about the FV solution, then you look at 4.5 section. Okay, and it give you the all the detailed aspect of this algorithm. Okay, what I just quickly brief you. Okay, so simple pressure, and that's it. Okay, so this is all about the controlling aspect of the OpenFOAM.